Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Daniel Harsono with us today. Hello, Daniel.
Hello, Frank. Thanks for the invitation.
Well, thank you so much for talking about your very lovely paper, which we're going to get to very soon. It's very nice. Very good one. And Daniel, where are you located at? Where's your wave function?
I am located at National Tsing Hua University in Hsinchu, in Taiwan.
Awesome.
At the moment.
Halfway around the world.
Yes.
What is summer like in Taiwan?
It's pretty hot and humid, but this year it's a bit mild. And at the moment, we're at the second typhoon that just passed by the north of us.
Yeah.
But we should be okay. But it's going to be rainy and windy the next 2 days or so.
Okay. And it is August, or at least my August 2nd. It's Daniel's August 3rd. As we record this, and it's good and toasty in Phoenix. We've had kind of a record heat length. It's not unusual for us to get up around 40, 42 C or something like that. But what is unusual is that it lasts for 20 days without a monsoon, the rain coming in. So, but we're doing okay, hanging in.
Yes, that was the headline of the news a few days ago. How hot it is. But...
Yeah, Phoenix is a poster child for the heat wave and everything associated around that. So yeah, very cool. And Daniel, what's your position there in Taiwan?
I'm an assistant professor here at the university, and I just started about almost 2 years ago. So yeah.
Very good, awesome. And Daniel, what do you like to do for research?
I'm mostly working on low mass star formation, disk formations, how the disk forms, and eventually now is working toward how the planets form and a bit of astrochemistry here and there. But yes,
cool, very
that's
cool.
Mostly what I work on, and lately I'm mostly focused on the water, how the water evolved from the early stages of star formations to the disk stages.
Yeah, that's a fun topic. Very cool. As is the one we're going to cover, which is going to bring us to this very awesome APJ letter. It is open access, people. We're in the open access area, and go grab a copy for free. Go get one. JWST peers into the Class 1 Protostar, the Taurus Molecular Cloud 1A, atomic jet, and spatially resolved dissociative shock region. And Daniel, take us away.
Yeah, so this is our latest results on the young Protostar JWST 1A. So now we have the James Webb observations that looks into the inner regions of this young source. So for this paper, we mostly focus on the outflows and winds. So that's the gas lines that's coming off from the inner regions of this the protostars.
Okay.
So usually the main highlight of young star forming region is the outflows that they launch from the innermost region.
Cool. Yeah. Very nice.
Yeah. So in this paper, we use the James Webb NIRSpec instrument, the IFU, to map out the whole entire regions from 1 to about 5 micron.
Cool.
So we will focus mostly on the atomic lines, such as the forbidden RN2 lines at 1.644 micron and also at 2.12 micron of the H2 line.
Okay, cool. Good.
So yeah, so let's start from the introduction to why we target this particular source.
Yeah.
Yeah, so of course this source was known to have a wind, as in revealed at the 12CO molecular line from using ALMA.
Okay.
So this particular source also have a known Capillary disk rotation. So from my earlier work and also from the later works that our groups did using ALMA, of course. So we know a hell lot about this source from at least spatially resolved observations in the submillimeter regime.
Right.
But the most puzzling thing about this source is that we couldn't find the jet. So every line, every gas lines that we looked at seems to indicate the wind component, and we tried to look for the SIO, which is a typical tracer for the jet component. That's the very fast component of the outflow and also very collimated. However, it's been unsuccessful and it's been non-detection so far.
Okay.
So this is why we wanted to use the GenSwap to see whether or not there is really a jet component in there. And if there's a jet, it should be in the atomic lines. And this is where the GenSwap comes in.
Cool. Good. I'm with you.
Yeah. So we're using the GenSwap NERSPEC instruments in the section 2, covering 3 filters like F100 LP, 170 LP, and 290 LP. So we cover roughly from 1 micron to about 5 micron.
Yep.
However, we use the high spectral resolution mode, so we have chip gaps in there. So there are certain sections of the spectrum that is actually missing due to the gap. So if you look at the figure 1,
oh yeah, let's go to figure.
Yeah.
Oh yeah, there's the gaps. You can see them.
there are gaps for sure.
Boink, boink.
And roughly in the inset, you see all the photometry points that have been covered by 2MASS and all the way down to Herschel points and also some of the ALMA points in there.
Nice, nice. Okay.
So we combined the GenSwap current observations in blue here in the inset with the Spitzer observations and also with Herschel from the Digit team, that's the dust, gas, ice team program with Herschel. So we pretty much cover all the different wavelengths at significantly high spectral resolution. And the part that is missing really for the source is the short wavelength below about 5 micron.
Okay. Okay.
Yes.
Good. Yeah.
So that's basically what is shown in the blow-up figure as the high spectral resolution part of this short wavelength.
Got it.
Where we see actually a lot of features from a lot of gas lines at like below around 1 micron. Those are real gas lines.
Okay.
And then some ice absorption features at about 3 microns, and also some at close to 4 microns and so on.
4, yeah. Okay.
Yeah. So yeah, for this particular letter, we only focus on the atomic lines below about 3 microns or so, and we're not going to cover a lot of features that are above 3 microns.
Okay. All right. Good.
So yeah, just to note, this is hot from the pipeline, right? So we're not completely sure about all the flux scaling here, but we did the best that we could at the moment.
Right. Fair enough. Fair enough. Okay.
Yeah. So if we can go to figure 2, then we can zoom into the some of the gas lines.
It's good. Look at it.
Yeah. Known. Yeah.
Okay, figure here. I'm
So,
gonna zoom it
yeah,
out.
and
Global. Okay.
Yeah, in the top part, we pretty much fit a polynomial to the overall continuum shapes, and then we try to normalize it to enhance the gas lines that are indicated, that are showing up in the spectrum.
Yep.
So these are the known gas lines in, at least I'm only having the hydrogen, the helium, the oxygen, and also some of the iron one.
Very nice.
So that's the most of the lines in there. And so we see a lot of the gas lines that are down actually about 1% to 5% of the continuum, but we will leave that for later.
Okay.
So, oh yeah, I completely forgot to shout out to all my co-authors, of course.
Oh, let's do that.
So this is so actually this is a project that was with Per Berkeley and John Ramsey, and we started actually, Per Berkeley actually started this program in the before the call of the first GenSwap. However, that call was postponed to the next year, and then I took it over. So Per is in Sweden. I think at the moment he's camping around Sweden somehow on
Arctic Circle, Arctic Circle.
Yes. And then John Ramsey is in Canada at the moment. And of course, there's a lot of help from Cosmo to be done at the STSCI to figure out how the pipeline works. And of course, and then we have Lars Gunson, Jes Jorgensen, and then Hannah Kalkut, Chiyun Lee, and Adele Tankut.
Very cool. It's very nice international collaboration here.
There's also one PhD student in Virginia that's actually working in Chiyun Lee, but he will do the rest of the analysis here. So just stay tuned for the rest of the analysis on the atomic lines.
Okay.
So the PhD student is Koras Osani, then if Koras, and then if you go to figure 2 again. So
yeah, let's go back to figure 2. Yep.
So he will look into the details on this other atomic lines, and we'll only cover a few of them in this letter. Yeah.
Yes.
So in the bottom part is zoom in into some of the major hydrogen line and also helium lines.
Yeah.
So we detected the spectrally results like the Passon alpha line, the Passon beta, and Passon gamma. In general, these lines are very broad, at least toward the center of the spaxel, so toward the center of the source. We see about 300 kilometers per second full width half maximum. That's really fast moving and very broad atomic line.
Yeah. Okay.
Even if we move to bracket lines, they're still very broad. So we are still seeing a lot of fast moving and hot gas in here.
Well, it tells a consistent story anyway, so that's good. Okay.
Yeah.
And you got some helium.
That's the helium line. Even the helium line is actually spectral result, and actually it is very broad here.
Yeah.
And it has the absorption feature in the middle. That's most likely due to the wind structure from the inner region.
Okay.
So at least these broad line features are consistent with the fact that the majority of the line is being emitted by something that is hot and fast moving.
Yes.
So it has to be something that is associated with wind or some kind of jet.
Cool.
Of course, usually the hydrogen line is being used for accretion tracer for the young protostars, even for class 2, so a more evolved disk. However, in this case, since the line seems to be very, very broad, the contribution from the accretion itself seems to be smaller than what is thought.
Yeah.
So this is what we try to do, try to disentangle between the winds and the accretion, but since the lines are super broad, at the moment we can only say that we are tracing a lot of the jets and wind component from these hydrogen and helium lines.
Fair enough. Cool. I'm with you. Very good.
So typically the helium line is also being used for accretion tracer on also a jet. However, usually those line feet, those spectral line profiles have much deeper absorption in the blue wing, and we don't see that deep absorption. So at least, unless that we're not seeing the fully spectrally resolved component, right? So we don't see the bluing absorption, then we're not completely sure whether or not we're tracing the accretion part from the helium.
Okay. Cool.
Yeah. So the nice thing with James Webb, we have the spectrally resolved component, and then since the NIRSPAC is an IFU instrument, we can go to figure 3, and we can actually look at the spatial distribution and the map of few of these lines.
Look at that. That's beautiful. Very nice. Beautiful. Okay.
So in the top left, we see the it's called the HST image that was taken in 1998, 1997, right, in the 160W filter. So it's about 1 micron or so.
Right.
And we see the James Webb 2 micron in the background in there. So it actually lines up perfectly.
Okay.
And this is how we align the images. We try to align the features that we see in HST with the James Webb features.
Okay.
And by looking at the longest wavelength of the James Webb observations, we try to align the ALMA observations. So the ALMA observation that is in purple there
Right.
is actually looking at the submillimeter disk component. And
There.
it's, I think that it is located offset compared to the overall scattered light.
Right.
So what we're seeing here in 2 micron, both James Webb and HST, is we're actually seeing the scattered light from the small grains.
Okay. Okay.
So we see all arcing up to the left. Is that left or yeah, arcing up to the side there, and that's all scattered light emission. And then if we move to B, we can compare this with the Passion alpha line and also where the molecular line of Toshio emission.
Okay. Okay. Mm-hmm.
So yeah. So we see the upflow component and what Alma was seeing. So it's really located deep where this component is located from A and B. So it's not very extended compared to the actually scattered light emission.
Okay.
So we think that the Toshio emission is actually looking at the wind, the disk wind that is actually launching off the Keplerian disk rotation, the Keplerian disk, right? But if you look at the hydrogen Passion alpha, it's actually very extended. It's much more. It's mostly coming from the scattered hydrogen line,
right?
That is from the inner parts. Yeah.
Right.
So of course, some of this could be actually hydrogen emission, but we still need to disentangle which ones are the scattered hydrogen lines, which part is the scattered hydrogen emission, and which part is actually the emission part of the hydrogen.
Okay. Okay.
Yes. And then moving on to the C part, and this is what was really what we really wanted to see was the forbidden RN2 line.
Yep.
It's really showing up in the highly collimated part of the source.
Yeah.
So now we're seeing atomic line coming from in the middle between the Toshio emission, and
right.
And that's pretty much what a jet component should look like.
Okay.
So we have the iron line that's very collimated in the middle of the source that is showing up as the jet component that has been missing from this particular target for a long time. And then, of course, we see the helium-1 line and also the oxygen-1 line. That's actually very compact and offset to the north side of the submillimeter disk. Right? So it's really in the center of that scatter light, small grains emission. So it's mostly in the brightest part of the 2 micron continuum emission.
Okay, right.
Yeah.
Very nice.
So usually this atomic line, helium and oxygen, is showing up regions where there's a dissociative shock. So we think that an outflow is launched from the disk to be molecular, and then at a certain point it gets dissociated, whereas the velocity is high enough, and also the gas temperature is high enough such that the molecules are dissociated. Yeah.
Very good. And you pick up the atomic. Very
cool. On the right part, now we trying to see the forbidden iron line and the H2 emission.
Ooh.
So this iron line is supposed to be the fast jet component that is highly collimated, while the H2 emission is always thought to be a bit more extended emission that is filling between the jet and also the outflow cavity. So between the jet component and the envelope part where the cavity opens up from the. Cool. So if you go to figure 4, then that's is it figure 4, the last figure? Then the cartoons roughly shows what.
There we go. There we go. Okay, who's observing what where?
Yeah. So usually young protostars are surrounded by a protostellar envelope, and the jet components and the wind is carving out an outflow cavity wall in the envelope. So it's like a strict conical shape. And these conical shapes are usually maintained by some kind of hydrodynamical turbulence that's inside inside the outflow cavity wall.
Okay.
And finally, we tried to see what really drives. The question has been like, what really drives the outflow? Is it the jet component? Is it mostly wind?
Okay.
It has been always thought that for young sources, young protostars, it should be the jet component that is really driving most of the outflow.
Yes.
But of course, for this source, that jet has been always not seen until now. So down, this is what we see, the iron jet component, and the H2 shock gas is actually surrounding the jet, surrounding the iron. So if we look at different H2 emission, it's actually much more extended than what is seen in figure 3.
Okay.
Yeah.
Yeah, because it goes much farther out. Yeah, yeah.
It goes further out usually.
Yeah.
Yeah.
Right.
But yeah, so different H2 emission, it can be very compact, close to iron, and lower transition of the H2 would be much more extended. So the cartoon pretty much shows like what we see. This the illuminated cavity wall on the left side of the disk. That's what we're seeing in the 2 micron, and also scattered line emission. That's where the H1 passion line is, and we see some extension of the helium line even in that side. And then, yeah, and then right above the disk, I think that's where all this hydrogen and helium and oxygen lines are actually peaking, and this is where the dissociative shock is actually happening.
Okay.
So at that figure at the moment, we see different knots. So we see other knots located in one location, and H2 knot location offset from the iron knot. So there's an offset between the iron and H2 emission. And then for the cartoon here, we're also showing where the ALMA is actually tracing the long baseline interferometry is actually looking at.
Disk in between the disk and the jet. Okay.
Yeah. So
I'm going to go back to figure 3 just to.
Yeah, figure 3 indeed.
Okay. So arc jet.
Yeah.
Cavity wall. Just scattering. Okay. Cool.
Yeah. So of course the main question here for iron H2 is that what is whether or not H2 is tracing the wind component, or is it actually tracing the reformed molecular line around the jet. Okay. So when the jet is launched, the gas along the jet could be hot, and then when it cools on the side, then molecules can reform again.
Right.
Yeah.
Cool.
Or the alternative, this is H2 that is really being launched from the wind component from the disk. Right. So at the moment, looking at the morphology, this is all we could at the moment, just looking at the map and see where the emissions are really picking up. We think that the H2 is really enshrouding the iron jet. So it's more like the H2 reform as the jet propagates through the envelope. Yeah.
Okay. Okay.
So that's what we found in this letter, and we tried to report our first results and the detection of the jet component toward this source TMC1A, where we mostly based an analysis on the morphology of where the atomic lines are located with respect to the ALMA molecular lines, and also where the H2 emission is located with respect to the iron jet.
Yes.
Yeah.
Very cool. Very, very cool. And there's 2 lovely appendices people, one on the centroid alignment, and there's one on BLT versus JWST.
Yeah.
So check those out. Very nice. Congratulations on your discovery of that iron jet. Very nice. Beautiful.
Thank you.
Thank you, Daniel. And you kind of touched on it a little bit as we were going through. And so let me push on that a little bit and ask, where do you think we go with this topic over the next, let's say, 2 to 5 years? Are there, for example, additional JWST observations in the pipeline? Are there other telescopes at other wavelengths, maybe another ALMA campaign? So just next steps, where do we go with this topic over the next couple of years?
Of course, we only publishing here on the NERSPEC component. We have the MIRI component that is being done by the GTO program.
Okay.
So I've seen some of the data there, but their team is working on it. So there are more atomic lines that we can use to disentangle between the wind and the jet component.
Okay.
So the GTO team also has a lot of sources that is being targeted in various atomic lines.
Right.
So the next step would be trying to look at different objects and see how they vary between young sources and older sources. Or and of course there's a GEO program being done on the jets and the upflows for binaries and also for single sources.
Ooh, nice.
So there are various programs that are looking into the uploads in detail.
Cool.
So I think that should be coming out in next year or two.
Nice.
Right? And then the next steps for this particular project is to have the PhD student to really look at in details of each of the various atomic lines.
Right. Yeah.
So we only publish some ratios between one atomic line to another to indicate the extinction, how much extinction in there, and whether or not we can extract the accretion rate.
Yes.
Because what we want is to know the accretion rate and how much is being ejected. And this still needs a bit more careful work that the PhD student in Virginia is actually looking at.
Cool.
So that's the next paper that will be coming out probably the end of the year or next year. Is the complete analysis of the atomic lines to see the extinction, the physical conditions of the jet, what actually the gas temperature, what density it is located at, where the density, the emission is coming off from. That's roughly going to be about a year to 2 years from now, of course. And then the next after that, we're going to have to compare these observations with theoretical models. Because there are simulations of winds and jets, and we need to move away from just looking at the rotations of kinematics. It's actually trying to see what are the physical tracers that we can compare between the atomic lines and also with the simulations. So there's in the pipeline to look at the simulations and extract the atomic lines, how strong they are, and whether or not we can get the same ratios.
Right. Very cool. Very cool.
So that's probably in more longer terms in terms of 4-5 years.
Very nice.
There's still a big.
That's the next PhD project. That's the next PhD project.
Exactly.
That's
cool. A PhD project by itself.
Yeah, it is. Yes, no doubt. Very cool. Well, I really look forward to seeing this topic evolve over the next couple of years. It's going to be very exciting to see this resolve in, and we'll learn a bit about protostars and how they do that. Very cool. Nice. Daniel, thank you so much once again for walking us through your very lovely article.
Thank you so much.
And that will do, everyone. And I hope this makes your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.